start from here. Okay, Ray, want to start. Hello everyone, my name is Parag Pal and today I am here to discuss about design of combined trapezoidal footing. We know that combined footing consisting of the four type rectangular, trapezoidal, strapping footing and raft footing. Okay, so that one of these the trapezoidal footing we are discussed today. Okay, for these notes please visit my website www.civilnotes.com. Okay, there you find out my PDF file and you can download this. Okay, so download that file and watch this video, then you can understand the both. Okay, so first of all I show the numerical. Design a combined footing for two column 3.6 meter center to center apart. Say 3.6 meter is a center to center distance between the column. Okay, carrying load of 850 kilonewton and 1100 kilonewton at a service. Okay, the size of column are 350 mm cross 350 mm and 450 mm cross 450 mm. Okay, this in this numerical 350 by 350 is my C1 column and this one is my C2 column. Okay, respectively 350 mm by 350 mm column carries a 850 kilonewton load and 450 by 450 column carries a 1100 kilonewton load. Okay, length of the footing is restricted to 5.5 meter. Here guys, there is some changes. If the numerical the statement is like that, length of footing is restricted to 5.5 meter, that means the footing is to be a trapezoidal footing. Okay, and when the width depth is to be given, width is to be given, then width is restricted. Okay, that width is restricted numerical, that line is called as that numerical delivers to the rectangular footing. Okay, if the width is restricted, that is a rectangular footing, and if the length is restricted, then it is a trapezoidal footing. Okay, now take SBC ship bearing capacity of soil as 180 kilonewton per meter square. Use M20 grade of concrete and Fe415 steel. Sketch the reinforcement detail. Okay, so this one is my numerical. Now I wanted to solve this numerical. Okay, first of all, C1 C2 we know what is the size of, this is size of column C1 and size of column C2. Okay, then C1 carries 850 kilonewton load and C2 carries a 1100 kilonewton load. Spacing between the column to column is 3.6 meters center to center. Okay, now length of footing is restricted to, that means total length of the footing is to be 5.5 meter. Okay, now that means design a trapezoidal combined footing. Okay, now what is the main principle of the trapezoidal footing? There is a CG of the column, that means a load coming for the column 1, load for the column 2. The CG of that column, okay, both column is coincide with the plane area of footing. It is one of the main principle of the trapezoidal footing. Okay, so first of all, my first step is that to determination of the dimension. Okay, so here, okay, length we know, spacing we know. So first of all, load calculation. Okay, in step number 1, that means we are calculating the basic requirement we want. Okay, so load calculation. In the load calculation, first of all you have to take the column load coming along with. Okay, so WA is a load from column A, WB column B load. Now 850 plus 1100 we add, this is a 1950 is a total load, but this is a working load of the column. Okay, not a factor load. Then add 10% of loading of self weight of the footing. Okay, so that means 195 multiplied by 0.10, so you get 195. Okay, so this one adding both load, then you get the total load as a 2145 kilonewton. Okay, but this is what working load, not a factored load. Okay, after that you have to go for the area of footing. How much area required for the footing? Okay, now we get the total load. We want area. Area, the formula given by total load upon SBC. Put the load, multiply by 1.5 for the factored load, divided by 180, which is SBC. Now this is mm square is the area of footing where your area of footing is to be constructed. Okay, now my next step is determination of the width. Sorry, Yes, width, both side projection, that means we are trapezoidal footing. Oh, trapezoidal footing, this one is smaller one, this one is longer one size. Okay, so this one like this. Okay, my reinforcement detailing show about all this one. This is my mistake that I am not drawn a diagram here for the representation, but at the ending there one is diagram. Okay, so you can understand. If you now see my notes, then please go to last page. There is my diagram and see this. Okay, so first of all, now I want to calculate this one, small projection of this side, width of this side. Okay, like this. Okay, this projection is like this. Okay, this is our topmost portion, not the depth. I am not talking about depth, I am talking about this one portion. Okay, this one portion. Now first of all, you have to area of footing. We know area of footing we calculated by total load upon SBC, but with the relation with the area of footing, we get some one equation, which is where the denoted the width of the footing. This side is called as A, okay, this side is called as A, and this side is called as B. So from the area of footing, I get one equation, that is to be A plus B divided by L by 2. Okay, where A and B are the breadth of left hand side of the footing. Okay, so sorry, breadth. Now put the area of footing which come from the last one formula. Okay, 17.875. Okay, now place, we don't know the value of A and B, we have to calculate this value. So put L, we know the total length, divided by 2. So you get the one relation A plus B. Okay, where it is, A plus B equals to 6.5 meter. Okay, this one equation number 1. Now next, according to the design principle, okay, according to, we know the where we wanted to CG of the load, okay, at a plane area. So according to the design principle of the trapezoidal footing, CG of the column load at x bar meter from the center of a column. X bar meter means this one, from this center, center to center distance to this distance. Okay, we have to calculate this x bar. So here x and xb, that means this x and xb, these are the projection. First of all, calculate this projection, but because of this, without this projection you cannot calculate the x bar. Okay, so xa equals to xb, which is calculated by total length minus spacing of ab divided by 2. So total length is 5.5 minus 3.6 by 2, so this is 0.95. So both are equal. Okay, but in the case of the rectangular, this is not equal. Okay, and in other case this is also not equal. Okay, this is 0.95. Now you have to put, now according to this diagram, see this equation, wb, that means this wb into spacing equals to wa plus wb multiplied by x bar. Okay, so I rearrange the value, x bar equals to wb into ab upon wa plus wb. I know that this relation WA plus WB from my load calculation. I place this value here. Okay, I place all value, I get x bar. Now x bar means this is the distance from this column of the center to this particular CG. Okay, now this one is the CG center, CG distance from the column. Now if you add 0.95, then you get the CG distance from this initial point. Okay, so here it must be coincide with the center of gravity of the plane area of footing. So xa plus x bar, as I told, equals to a plus 2b by a plus b multiplied by L by 3. Or this one is the equation. Put all this value, a plus b value, put this value. These are the most separate. Use this one. Okay, very easy. Put the value all in a calculator. Okay, put shift only a plus 2b is not put in a. In the case of a plus 2b, you place the shift x, that means plus x in the calculator, you get the value of a plus b equals to 10.56 meter, sorry. Okay, so now both equation you have a plus b equal to and a plus 2b equals to, solve simultaneously in a calculator, you get value of a and value of b. Okay, up to this mark I think everything is clear. Now you get the breadth. Okay, length you know already, spacing you know, CG up to the CG distance you know from the initial point. Now we get proceed for the next further calculation. So further calculation is for the upward soil pressure footing. Always upward size footing, the given SBC which is less than the given SBC. Okay, so for that we have a formula like this, P equals to column load upon area of footing. Column load is factored load you have to take. Area of footing, it is 163.63, which is less than 180. 180 is over SBC. Okay, which is in a kilonewton per meter square. So that here is the same. Now you have to go for the calculation of Bx, Vx, Mx. Now what is this Vx, Vx, Mx? Actually this is a main form of the trapezoidal footing. In every footing, you have to calculate the shear force and bending moment diagram. Without that, you cannot provide the steel, because the what amount of bending is to be there, then and only then you can provide the what can I say, the steel. Okay. For that, to determine the shear force value and to determine the bending moment value, there is some expression we have to calculate from this diagram. Okay. So the diagram representation is like this. These are the bread. This is the topmost portion. Okay, topmost surface. A portion. This is total B portion. I divide B minus A by 2. B minus A by 2. This is Bx. This is small distance y. Okay, so using this equation, first we have to calculate Bx, then we calculate Vx, then we calculate first we calculate Bx, then we calculate Afx, area of footing at this xx section. Okay, we place one section here, xx section. At that section we are calculating the value Bx, Vx, Mx. Okay, so first we have to calculate the value of, sorry, that's my something wrong. So first you have to calculate the value of Bx, then you have to calculate the value of Vx, then calculate the value of Bx, Ax, Vx and Mx. Okay, let's calculate. Okay, so what is Bx here? Bx is nothing but this breadth A plus twice y. Okay, simple equation. Now you have to use the similarity of triangle to calculate the value of y. What is the value of y? We have to calculate here. So by using similarity of triangle, y by x, okay, y by x is equals to b minus a by 2 divided by total length. Okay, so place this 2 at the bottom. Okay, solve the numerical, you get the relation in the form of y equals to 0.15x. Now you place the 0.15x in the Bx formula here. 2 get cancelled. Okay, Bx equals to a plus b minus a by l into x. Put the value all, you get the relation Bx equals to 2.42.0.302x. This is one equation. Now we are using this equation for the calculation of area of footing at particular xx section. So the formula is like that: a plus bx divided by 2 multiplied by x. Put all the values here. Okay, you get the area of AF6. Okay, area of footing at particular xx section. Now you have to so now area footing of x we get here. Now then we go for the upward pressure reaction due to the load on AFX. Okay, upward pressure reaction we calculate, which is less than 1 SBC. Okay, now Vx is used for calculating the shear force value. Okay, so Vx is nothing but upward pressure intensity multiplied by area of footing at xx section. Solve this numerical. Okay, you use this numerical, don't solve this numerical, this is very okay. Okay, if you wanted to solve this numerical, you can solve this, because for further calculation you have to put Vx as it is. Okay, now very easy numerical, which is not very so much hard. Then for calculation of bending moment value, you have to integrate the Vx from 0 to x limit. Okay, so you get the value of moment of x. Okay, now Vx and Mx very important for calculation of the shear force value and bending moment value for the particular loading comes on a trapezoidal footing. Okay, and Bx and Afx also important, but without our Bx and Afx you cannot calculate this value. Okay, so there is only two formulas and somewhat minor relation which is used to calculate Afx, Vx and Mx. Okay, now for further calculation we are going. Now here we are calculating shear force calculation. Okay, shear force means we are getting here Vx. And now we have to calculate the shear force at particular distance. Okay, remember we take projection as 0.95. This is for 1.5, this is for one value, one distance. Now then we calculate the shear force at the CG point. Okay, then we calculate the shear force at the last column, but the distance is like this: 5.5 total length minus projection 0.95, so it is 4 point something. Okay, so it is very easy understanding. First of smallest distance, then up to CG distance, then total distance. Okay, now first we calculate shear force at 0.95 under column A. So put the value of x as a 0.95 in this equation. You get the value of shear force at left of column A. Okay, now you want the shear force at right of column A, then just the load coming along 850, which is working load, multiply 1.5 made factor load minus that shear force at left A plus minus, because this load is going downward direction, minus from the shear force at right A, you get the shear force of the right A. Okay, now then we want to calculate the shear force at column B. So place 5.5 total length minus last projection. So it's 4.55. You get the shear force of left A, then shear force at right A. Very easy. Okay. Now you have to see where the point of zero. Okay. You have to see now where the point of zero projection is to be there, where the point of contraflexion is to be coming around there. Okay. Shear is to be Vx equals to 163.64. Okay, Wa, just you have to put the value of Wa and solve this equation by quadratic form. Okay, x square plus, okay, you get that. So you get the value of x equals to 2.75. Okay, multiply Wa by this, so you get the value of x as a 2.75 and solve this equation from here. 163.64 equals in bracket 2.42x plus 0.15x square minus. Now you get all the shear force value. Okay, now we are proceeding for the bending moment calculation. Okay, same bending moment calculation, but you have to use the mx equation here and put same at particular distance. X equals to 0.95, x equals to 4.5, and x equals to what, 2.75, where the zero, where the point of contraflexion is to be coming around 0. Okay, so here, okay, now the diagrammatical representation is like this. This is your the value, shear force value, here 0, and this 2.75 distance. You get the bending, maximum bending moment here. Now you have to use all this bending moment to calculate the steel. Okay, now next step is here that you have to design a longitudinal reinforcement. For design a longitudinal reinforcement, there are some, I made this table. This is very easy, because if you go separately for each and every under column A1, under column A and B, between column A, B, and under column B, then your calculation is getting too long. Okay, this is very simple process. Just made one column and calculate on a calculator. It saves your time and is very easy. So first of all, take it out the bending moment. Okay, which is the factor bending moment. Okay, obviously you have to solve with the factor load only. Then bending moment is here, breadth bx is used here at particular distance. X equals to 0.95, x equals to 2.75, and x equals to 4.55. Put with the using all this value, you have to calculate this AST requirement. Then you go for the minimum AST according to IS code, this formula. Then take actual AST, that means maximum from this 3 and 4. Then provide the number of bar, that means diameter of bar you have to provide. Then number of bar is here. Then AST provided, that means how much 8 bar of 25 mm diameter you providing. So what is the steel area of the steel is coming around, this is AST provided here, and percentage of AST is which is used for the calculation of the tau c and tau v to take the, it is a shear force, shear like providing. But here I calculate, then here tau v nominal shear is greater than tau c. Okay, so here no need of shear, so we are providing nominal shear here only. Okay, now go for the depth of footing. Depth of footing is really equation very easy. Moment at maximum equals to 0.138 FCK BD square, but B is BF here. So BF as 2.75 you have to calculate first, because there is a maximum bending moment. So put the value of X in the BX numerical. Okay, you get the value of the value. Then put the value is here put the value of x, that's mean this BF3240 in the form of you get the D. Okay, now check for the punching shear. Okay, punching shear is a or perimeter multiplied by load per perimeter multiplied by depth. Punching load you have to calculate tau b tau c. Check it out, here is same. Our nominal shear force is greater than shear force, so it is same. Okay, now go for the transverse reinforcement. Same table you have to make here: upward transverse reaction, transfer projection, cantilever bending moment, transverse length, AST spacing, and actual spacing provided. So use all this value. Just first off use this value, then use this value. Okay, using all this value you get the bending moment, then transverse length a0 and b0 noted in the diagram, then spacing. And spacing I use normal formula. Okay, a phi, here a phi is the area of one steel. Okay, which is 12 bar steel. 12 bar area, one 12 bar steel area is A5. Okay, then here the diagram where you can, this is A0, this is B0, the projection is to be here, weight, load. Okay, now you have to go for the reinforcement detailing. So along with my data coming around the longitudinal and transverse reinforcement, I noted down here. This is my final output of the numerical, and hope you like it. Please download this PDF file from my website www.civilnotes.com and then watch this video come with matching with this video. Then you can understand very simply and you can understand better than me. Okay, so thank you. Keep watching, keep learning. Bye.